Okay, wavelength and frequency problems. Can do. Was there one in particular that you saw, or because I think one of the questions was related to the wavelength and frequency stuff, but I'm trying to remember which one. If you can find a specific example, it'll make it a lot quicker for me to pull something up. I mean, I can do a general review, but let me see if I can get the, give me 1 second. I'll pull up the green sheets too. Okay, so no specific review problems. All right. So the basics. Give me 1 second. Okay. There's only two real equations they throw at us with wavelength, frequency, that sort of thing. But there's a couple of things with which you have to be careful. First one, hold on. Same with my mouse. Actually, here. Make this a little more size. Alright, so basically the two equations you see up there are energy equals Planck's constant, and then you've got this nu. Now you got to be careful with nu. It looks a lot like a V, and if you're not careful, they could be using a V instead of a nu, but in anything that pretty much has to do wavelength frequency, it's that little bent over V, so it's a nu. Alright? Planck's constant's given to you there. It's minuscule, but then again you think you're talking about per individual particle. So once you take that and multiply by 6.02 times 10 to the 23rd and get the number of molecules, if you're talking about a whole mole, now you're significantly larger and you're getting into a decent size unit. So basically, let's go to the absolute simplest. Alright, wavelength, you already know. Alright, wavelength, they give it as lambda. Frequency, if you have two waves, I should have used different colors, but if you can imagine moving along both of those waves, you're going to strike this one more often than that one's if they're moving at the same speed. And all light waves move at the same speed. Now, if at any point you have a question or think of something, or if this is too rudimentary, just, type it since we can't actually talk. Alright? Now, the things with which you have to be careful. Energy, sometimes they'll ask for the energy per mole of photons, or per mole of a substance. Or sometimes they'll ask for the individual particle. Alright? So again, if you look at Planck's constant, 6 times 10 to the negative 34th joules per joule seconds. Okay, the reason that's that weird unit joule seconds is because nu is actually given to you. Let's give nu a little color here. Nu is actually given in per seconds or waves per second. And so then the energy units come back and you just get joules because the seconds cancel out. Alright, sometimes they'll say this is joule seconds per wave or waves per second, but usually you'll just see joule seconds and this will just be given in a unit of per seconds. So the energy unit comes out to be joules. Now, again, careful whether it's a per particle or per mole. That's the one thing that'll major difference. Alright, that's why here, this is about the only place you see Avogadro's number actually being mentioned. It's the how many per mole, and really the only place you're going to use it is probably something if they do give an energy question. Now the other major equation, C equals lambda nu. Alright, that's badly drawn, but you get the idea. Speed of light within our tolerances is constant. It's not really constant. You can slow it down or speed it up slightly as it goes through a medium, but we don't care. It's basically 3.0 times 10 to the 8th meters per second. And again, lambda, here's the kick in the head. You got to be careful with lambda because lambda can be given in meters. That's awfully small. Apologies. Let me just go to a desk camera since you have those, and we'll open up the other when we need it. Alright. Lambda can be given in meters. Highly unlikely. Much more likely that it'll be given in nanometers. And nanometers are 10 to the negative 9th. Alright. A nanometer, 1 nanometer is 10 to the negative 9th meters. So if you're given it in nanometers, now you've got to convert your wavelength. Alright, to meters. Very important. Divided by 10 to the 9th. Alright, and then nu again should be given in per seconds. I mean, they could get bizarrely weird on you and throw something in per minutes or per hours, but I highly, highly doubt it. Alright, so the big thing here is making sure that your units are consistent, and the big thing up here is making sure whether you're talking about per mole or per individual atom, or molecule, or whatever it is they're talking about, or photon. Did that help some? I'm just making a note to remind myself to edit this down to just that bit. Let me see if I can track down a problem. Okay, the question is, when it asks you to find the energy per particle, do you multiply the moles by Avogadro's number to get the particles, and then divide the joules by the particles, or is it something else? I think you just nailed it. Let me think about that, change it from words to something. So, yeah, if you were given that, say, 2 moles of photons produces blah energy, then that would be 1.2 times 10 to the 24th photons produces blah energy, and so to find the energy you divide by 1.2 times 10 to the negative 24th photons, or whatever, and that would give you energy per photon. Yeah, I would agree that that would be it. while you're thinking, I'm looking for a representative problem. Okay, let me throw this one out. This will bring in a couple of things. I'd have to shoot this down. And as this is, I would think this is large enough that you can still read it even if I shoot it down to get it all in one frame. Is that too small to read? Okay, maybe we just try this one and it'll bring in P's as well as one way they might throw the wavelength frequency type stuff at you. So give this a shot and then I'll walk you through it after you try it. I think that might be a good use of our time. If somebody is watching this video later, my suggestion would be to pause the video, work the problem, and then fast forward through till things start moving again, and you'll know it's been a heck of a day. Let's walk through this problem correctly. All right, from the top. You still with me, Aiden? And patient, and I apologize. Alright, from the top, what's the timestamp so I can actually do this right? 1 hour, 2, okay. Alright, so looking at this problem, let's make the problem larger. Alright. So the basic problem we have is, it says the complete photoelectron spectrum is given. For the first part it says to generate the spectrum a source capable of producing electromagnetic radiation in the range 7 times 10 to the 4th kilojoules per mole. Such radiation is from which part of the spectrum? And then it asks us to justify. Alright. So we're given 7 times 10 to the 4th kilojoules per mole. Alright? Which we have to immediately convert to use joules, which would be 7 times 10 to the 7th joules per mole. Reason being is there's 1,000 joules in a kilojoule, so the unit gets 3 times bigger. Now, we have 2 possible resources. we can use either C equals lambda nu, but we were not given a wavelength. We can use E equals Planck's constant times nu, and we do have both of those things so that we can make that work. So we've got E equals Planck's constant times nu. We're trying to solve for nu, so we're going to have nu equals E over Planck's constant. We were given the energy as 7 times 10 to the 7th joules per mole, and we were given Planck's constant to be, apologies, I should have that memorized, 6.626 times 10 to the negative 34th joule seconds. Alright, now if we run this out and we do the math, we get 1.06 times 10 to the 41st. Now, the important thing here is, the thing that I want you to notice is that our units aren't right. The problem is we've canceled all joules. What we've got now is we've got per moles on top and seconds on the bottom, or our unit is now 1 second mole, which is not okay because we're talking about an individual particle. So what we've got to do here is we've got to go, alright, so we're going to take that and we're going to divide by Avogadro's number, because this is for a whole mole of them, is this in per seconds per mole, divided by 6.02, apologies, 6.02 times 10 to the 23rd particles per mole. Now, why that works out is because now we've got 1 over moles over 1 over moles. The 1 over moles cancel, and we've got frequency per particle, and the frequency per particle works out to be 1.7 times 10 to the 17th. And if we look at the problem, 1.1 times 10, or 10 to the 17th, falls in the X-ray category. Okay. Now, for the other two parts of the problem, a student examines the spectrum and proposes the second ionization energy is this. To refute it, what subshell did it come from and what subshell corresponds to the second peak? Alright, now let me make that a little larger so that you can see what we're talking about. Alright, so it says that he proposes the second ionization energy is this. Now, if we look closely at this, let me bring it down. How many electrons? Which electrons are where? Well, first ionization energy is going to be to take one of these electrons off. Second ionization energy is going to be to take another one of these electrons off. Alright? Because, how's this set up? This chart is set up largest to smallest. So to come back to the desk, this is like 10 to the 5th. This was given to you something like, 6 times 10 to the 4th. And this one is given to you, 10 to the 3rd. And this is about 2 times 10 to the 3rd. Alright? So to take that first electron off, it asks the following: to refute. They're telling you right now with their words to refute, they're saying it's wrong. They're telling you flat out it's wrong. If they use the word to refute, they're saying show why he's wrong. Alright, so the subshell from which the electron is removed in the second ionization of an atom. And the subshell that corresponds to the second peak in the photoelectric spectrum. Okay, so first electron is going to come from here. What subshell is that? 2p. Alright, then it says the subshell that corresponds to the second peak in the spectrum is what? 2s. Okay, so all they're saying, that's all they're asking you to do. Now, here's the thing. This is an incredibly easy problem if you're careful about it, because it says just identify. That's all they're asking you to do. It doesn't ask to explain, it doesn't ask to do anything, it just says to identify. And so what you're doing is, where are you taking the first electron from? You're taking the first electron from the 2p. What would be the second ionization energy? You would also be taking it from the 2p. Okay, then they say, what peak is this? That's the 2s peak. The second electron's not going to come from the 2s peak. Alright, does that make sense? Those of you watching this at home, we have about a 30-second lag between the time I say something and the time anybody's able to type a response. Alright, well, this has been about an hour. Is there anything else that I could do with this problem, or anything I can do to help? And I apologize for being a little scattershot today. Not really used to working from home still.